So this chapter is about equilibrium of a particle, and this chapter is divided into 4 sections. The first section is about equilibrium of a particle. So we will define the conditions for equilibrium of a particle. The second section would be on free body diagram, which is also one of the most important topic of engineering mechanics statics. The third section would be on coplanar forces. We will discuss forces in 2D plane. And the third section would be about 3D force system. Okay, so a particle is said to be in equilibrium if it remains at rest, if originally it was at rest, or has a constant velocity if originally it was in motion. So basically, what it says is that a particle is said to be in equilibrium if it remains at rest, or at uniform motion, which is constant velocity. Now, for a particle to be in equilibrium, it has to satisfy Newton's first law of motion. That is, summation of all the forces should be equal. Now, Newton's second law says that if there is a force, then this force will produce an acceleration on the mass. So, in order to be for a particle to be in equilibrium, the acceleration has to be zero. And the only way acceleration will zero is that the summation of all the forces acting on a particle would be zero. So this is a condition which needs to be satisfied when we need to see conditions for equilibrium. Okay, so how to find forces, how to know all the forces are zero or not, how to figure out if a particle is in equilibrium or not, we use this free body diagram. So a free body diagram is actually a drawing that shows the particle with all the forces that act on it. So in order to know that if a particle is in equilibrium or not, we need to know if the summation of forces are zero or not. So in order to figure out this, we need to draw a free body diagram. So we can draw a free body diagram in 3 simple steps. Step 1 is to draw an outline shape. So imagine a particle to be isolated or cut free from its surrounding. This requires removing all the supports and drawing the particle outline shape. So what do I mean by that is, for example, let's just say you have this crane, right? You have this crane and the crane is lifting this weight by a cable. So if we are interested in that, is this thing in equilibrium or not, then we have to isolate this. How we can isolate this is that we can remove all the other things and we can just isolate this crane sort of a thing here, and this can be represented in free body diagram as a particle. Now the second step would be to show all the forces. Now indicate on this sketch all the forces that act on the particle. These forces can be active forces which tend to set the particle in motion, or they can be reactive forces which are the result of constraints or supports that tend to prevent motion. So basically there are 2 types of forces, active forces and reactive forces. There are actions and there are reactions, and we'll go into more detail in chapter 7 when we'll study internal forces. But for the matter of this example, we have this trolley and the active forces is weight that is acting on it, that is weight W. And as a reaction, this body is not going down because you have this cable and the cable is pulling this upward. So you have a reactive force from the cable, and I can name this reactive force as T. So first step was to draw an outline shape. We drew an outline shape. The second step was to show all the forces. So we have shown all the forces that are acting on this body. Now the third and last step is to identify each force. Now the forces that are known should be labeled with their proper magnitudes and directions. For example, if we know how much is the tension, for example, the tension is 2 kilonewton or something, so we will put the value of that force. But in our case, since we don't know the values of T and W, so if you don't know the values of T and W, then you can just put the letters instead of values. So finally, if I want to draw a free body diagram of this particle, so first step was to draw an outline shape. Second step was to show all the forces. And third step is to identify each force. That is, if we know the magnitude of the force, then we can write out the magnitude of force. But right now we don't have the magnitude of the force, so this would be our free body diagram for this example. Okay, so the third section is about coplanar force system. So coplanar force system includes a force system that is acting on a particle but in the same plane. So what do I mean by that? So it's a basically two-dimensional force system, coplanar force system. That is, all the forces are acting on the same plane. So basically it's a 2D system. So this is one dimension. So this is the second dimension. So all the forces are on this plane. So if all the forces acting are on the same plane, then this type of force system would be called a coplanar force system. For example, this is an example of a coplanar force system. You have a particle, and that particle has four forces acting on it in a x and y axis. So this type of system is called coplanar force system. Now the condition of equilibrium is that all the summation of forces should be equal to 0. So this is the condition for equilibrium. So if we are saying that this particle is in equilibrium, then it has to satisfy this summation of all the forces is equal to 0 condition. Now, before we have learned that all the forces equal to 0, it would be very difficult to find. We can find, but it would be little bit difficult to find the resultant of these forces. But if we divide, or if we break down these forces into horizontal and vertical components, and then we will have these perpendicular components, and it would be easier to do the summation of all the forces and figure out the forces if this is in equilibrium. So what would that mean is that we can also write it down in terms of two equations. One equation is summation of all the forces along x-axis is equal to 0, and the second condition is all the forces acting on the y-axis is equal to 0. And we can also write this down in terms of Cartesian vector system. So this is basically the same as this one, but this one is written in the form of Cartesian vector coordinate system. So for example, you can also write summation of f of x plus summation of f of y is equal to 0, which is this condition, and you can also put I and j, and that would be the Cartesian vector coordinate system as we have discussed in previous lectures. Okay, so now let's just do one example. So in this example, this is also a coplanar force system. That means that all the forces are acting on a plane. There is no three-dimensional force system. So now it says that determine tension in the cable. So we have to figure out the forces in the cable. So there are 3 cables, and we have to find out what are the forces in these cables. And the given is we have 60 kg of mass at D. So D is equal to 60 kg. So this weighs 60 kg actually. Now kg is a mass, and force would be equal to mg, because this weight will act on it, and that weight can be calculated as mg, and mass is 60 kg and weight is 9.81 Newton. It would be the total, so which is written here. And same force, so this would be the tension force in this cable. Not in this cable, but this is the weight, and we have one component which is acting on this. So in order to figure out the tension in the forces, given that this whole system is in equilibrium, so if we say this whole system is in equilibrium, we can write down summation of f is equal to 0. We can write it down in this way if this is satisfying the equilibrium condition. Now you can imagine, like, you have three forces, and let's just first draw free body diagram. So let's just say this is the particle, this is the particle, and you have force 1, force 2, force 3. Now the first step was to isolate the particle. We isolated the particle. The second step was draw all the forces which we know. So we know there are three forces, three cables, so we have drawn three forces. Now the third step is to write down the values if we know the values. So let's just say I'm gonna call this TBD, and this is 60 into 9.81 Newton, this one. And this one is TC. We don't know what's the value. We have to find out the value. So we're gonna just write this letter, and this is TA, and we also don't know the value. Now we know two conditions of equilibrium: summation of f of x is equal to 0 and summation of f of y is equal to 0. Now summation of f of x is equal to 0, it means that we have all the components that are acting on horizontal or x-axis. We can write it down and the summation would be 0. Same would be for the vertical forces. Now how many forces are acting on horizontal and how many forces are acting on vertical? Let's just try to find out this. So you have x-axis, let's just say it's an x-axis, this is y-axis. Now this component can be resolved into its rectangular components, this one and this one. So this would be TCX, this would be TCY, and similarly we can do this. This would be TAX, this would be TAY. Now we know that this is 45 degrees and this is 3, 4, 5. This is 5, this is 3, this is 4. Okay, so there are two forces that are acting along x-axis. One is this force, one is this force. Okay, so this force is, I'm gonna write it down here. So this force is f of x. So I'm gonna, this is TC cos of 45 degree, because this is a horizontal component and we know f of x is equal to f cos theta. So this is cos theta and theta is 45 degrees. So this is TC cos theta. Now this force is on the opposite side. So we will put minus, and this is TA. And if you do the math, because if you want to know what is the horizontal component, so horizontal component is cos, right? Cos theta is equal to base over hypotenuse. So what is the base in this case? The 4 is the base. What is hypotenuse? 5 is the hypotenuse. So it would be 4 over 5 is equal to 0. That's the condition for horizontal forces equal to 0. Now for the vertical forces, there are, this is one vertical force, this is two vertical force, and this is our third vertical force. So I'm gonna write it down, the equation of equilibrium for vertical forces. TC, this is the TC, and TC would be sine of 45 degree because it's a vertical component. And then we have perpendicular over hypotenuse for TA because it's a vertical component, and in upward direction you have positive, so weight is acting downwards, so you will put minus, and then you will put 60 into 9.81 Newton is equal to 0. So this is our first condition, this is our second condition. Now if we solve this, we have to solve all this, right? So how to solve this? We can just put one thing. For example, let's just say if we're gonna solve this, we can, because we have two equations and we have two unknowns, TA and TC. So we can solve these two by simply using these two equations. So if we use these two equations, we will get TC equal to 475.66 Newton. And we can put it in another equation to calculate TA is equal to 420 Newton. So that's how you solve these coplanar force systems. Okay, now let's move towards 3D force system. Now a three-dimensional force system includes forces acting on a particle in three different dimensions. So it's a bit more complicated than 2D force system. So let's just take an example of this. You have now instead of 2 dimensions, you have 3 dimensions. You have x-axis, you have y-axis, you have z-axis. And all the different forces are in one of the 3 dimensions. So same for a particle to be in an equilibrium state, you can calculate by summation of all the forces is equal to 0. But in this case, we have 3 components. So you will have 3 equations. Summation of f of x is equal to 0, summation of f of y is equal to 0, and summation of f of z is equal to 0. Similarly, you can use Cartesian coordinate system to calculate the summation of forces is equal to 0 by using I, j, and k vectors. Now let us go towards one more example that would include 3D force system. So in 3D force system, you have 3 coordinate systems. Now we have to figure out forces in the cables. So there are 3 cables. One is this cable, one is this cable, and one is this cable. So we have to figure out what are the forces in these cables. So what is force in D, what is force in C, and what is force in B. And A is basically downward direction. So we have 3 equations. Summation of f of x is equal to 0, summation of f of y is equal to 0, summation of f of z is equal to 0. So what is summation of, because this is the force, so these are the components. So this would be one component of D, this would be another component of D. Similarly for C, this would be one component of C, this would be another component of C. So in this way, we can try to resolve all these components into all these 3 directions, and then we can solve for the equation of equilibrium. So let's just try to see how many forces are acting along x-axis. So one is pretty clear, this D. This is the component of D which is acting on x-axis. So let's just try to resolve this one. So we have 30 degree here. So this is the component with cos of 30 degree. And so this would be the component with sine of 30 degree. So this is f of x component and this is f of y component in this case. So we will write fd sine of 30 degree because it's on the y side. So it looks opposite because if this, or you can also write f of d cos of 60 degree, depends, because this is 30, so it would be 60 degree, and you can also figure out this way. But for now, I've written f of d sine of 30, and which is the another force which is on the x-axis. I see this has one component and 2 components. So it's one component on x-axis and another component is on z-axis. So we can, using this 3, 4, 5, we can write minus 4 over 5 into f of c is equal to 0. So this is horizontal component force. Now, similarly, let's figure out how many components are acting on the y-axis. So this is a y-axis, right? So this, we have this force, which is minus fd cos of 30 degree, plus we have another component, which is this one, which is acting on the y direction. So this would be f of b is equal to 0. Now, which component is acting on z direction? So for d, no component is acting on a z direction because D is on x y plane. And yeah, so this is the z plane, and on z you have this force and you have a component of c. So if I write it down, for component of c in the y direction, you can say 3 by 5 f of c minus you have a weight which is 90 pound is equal to 0. So you have equation 1, equation 2, equation 3. If you solve all these equations, which you can do easily, and let me give you some example. For example, let's just take this equation 3. So if you want to find FC, it would be pretty easy. FC is equal to this 90 will go there. So it's 90 pound, and then this 5 will go there. You will multiply by 5 and you will divide by 3. So FC is equal to 150 pound. This is our FC. So FC is equal to 150 pound. Now all you have to do is to calculate FB and FD and FC also. We have found FC already. Okay, so we have FC, so we can use this equation, right? So FD sine 30 degree minus 4 over 5 into 150 is equal to 0. So you can solve this, right? If you solve this, you will get FD is equal to 240 pounds. So you have FC, you have FD. All you have to do is you have FD. So you can just use equation 2 and you can calculate FB, which would come out to be, just solve this. You have, this will go there, and FD multiplied by cos 30, basically 240 multiplied by cos 30. So if you multiply 240 with cos 30, you will get 208 pound. So that's how you solve the system of 3D force system. So you have multiple forces, you break down into their Cartesian coordinate systems, and then you can use equilibrium equations to solve the unknown forces. So this is chapter 3, and see you in the next chapter.